Good morning. It's a pleasure to announce Professor Ofer Zeitouni from Department of Mathematics of University of Minnesota in the USA and Technion University in Israel. He's going to talk about random matrices and large deviations, and his areas of interest includes at least stochastic process and filtering theory with applications to communication and control, applied probability, large deviations, and random matrices. He's visiting Brazil to participate in the Colóquio Brasileiro de Matemática, as you can see for yourself, and also to the meeting next week in probability, which is going to happen in Angra dos Reis. So it's a pleasure to have you here. You are on. Thanks for coming.
Thank you very much, and thanks for the invitation and the opportunity to visit here. Of course, I've heard about Rio and IMPA many times before, but it's my first, and I enjoy it very much. So, this is a somewhat abbreviated title, and most of what I'm going to speak about today is based on joint work with Alice Guionnet, and to a certain extent what I'm doing today is a warm-up play before the real thing, which would be a course by Alice Guionnet next week at the same probability meeting. So all those of you who are interested and decide that this is what they want to learn, there will be a 6-hour course covering essentially what I'm going to cover today, or parts, I mean a little bit more, but not much more. Okay, so that's actually, let me be consistent. So this is a plan of what I want to talk about today. I want to tell you something about matrix models, where do they come about, what exactly it means. Then I will relate it to certain integrals over the unitary or the orthogonal groups. And the main question in the resolution of these matrix models will be to understand well the asymptotics or the logarithmic asymptotics of this kind of integrals that I call Itzigson-Zuber integrals after the physicists Itzigson and Zuber, who first looked at that from the point of view from the physics motivation. Then I will introduce the tools needed to do this, to carry on this study, which are different from what physicists and others have used before, which are the tools of stochastic calculus and large deviations. So of course, I will not do a crash course in stochastic analysis and large deviations, but I will tell you the essentials of what is needed. I want to put it all together and to show how this study leads to some interesting PDE type questions that actually are not resolved at all and are an area of current interest and research. Okay, so that's the basic plan. And let me start by describing what are matrix models. So the idea is to look at n by n matrices, real or complex, is not so important, but in any case, they will be either symmetric or Hermitian. So in the real case, let's focus on the real case for a while. The matrices A1 and AD are supposed to be n by n real symmetric matrices. And then, taking the Lebesgue measure on the entries, you put a joint law on these matrices described by this function Q, by the density Q that I wrote above. So Zn is, of course, the partition function. It's a normalizing constant that is needed in order to make this whole thing normalized to total mass 1. And P is some polynomial that describes, so the easiest case and the simplest case you should focus on first is the case that P is just a sum of polynomials in one variable. So P of A1 up to AD is just A1 square plus A2 square plus AD square, in which case what you find there is just a Gaussian law. It's just a law on these matrices with Gaussian entries. And this has been suggested many years ago by physicists as a way to enumerate random surfaces and for other applications. So let me just make one quick link with that. That's not really the focus of what I want to describe to you, but maybe it is worthwhile to briefly mention the link. So let's focus on the case without interaction first. Sorry that this is not as neatly printed as the previous slide. So let us look at the simplest case where xn is what I call the Vignale matrix. So what does that mean? It's a symmetric matrix, n by n, whose entries have the law, whose entries, except for the symmetry constraint, are independent, and have the law, they are Gaussian on the off, on both the off and on diagonal entries are Gaussian, and the variance is slightly different on the diagonal and off the diagonal. And suppose what you want to do is to compute moments of this matrix, or moments of traces of this matrix. This, of course, is related to the spectral measure of the matrix Xn. So this information about moments, traces of moments of Xn, tells you something about the spectrum of Xn. And these matrices are called Vignale matrices because Vignale was the first to prove that if you take such a large matrix, you look at the spectrum as a dimension goes to infinity, this spectrum converges to what is now called the semicircle law or Vignale Semicircle Law. So that's just if you plot, if you wish, you plot a graph of the eigenvalues, the cumulative distribution of the eigenvalues, what you find is the semicircle distribution, so a given distribution. And the way that Vignale did this computation, he actually computed all moments and showed that asymptotically the limit of the moments are the same as the moments of the semicircle law. So suppose you wanted to do such a computation. Suppose you wanted to compute the fourth moment, say, the trace of xn4. Then, of course, you can rewrite it as a certain product of entries of x, which I have rewritten here. And then you use the fact, if you're dealing with a Gaussian case, you can use the fact that for Gaussian random variable, the expected value of any product, you can rewrite it by Wick's law as products of expectations of two entries, which is just reminded by this particular rule in the case of four random variable. You take all possible pair combinations, you sum them up, and you get that. And there is a systematic way to do that, coming under the name of Feynman diagrams, that allows you to do this computation in the Gaussian case. And now, if you do that, what you realize that these terms here, you can draw them as diagrams. So let me now draw the diagrams. Forget for a moment what is written here on the left. So for each, you have four indices, I1, I2, R3, and I4. So if you draw this little thing, what you need to do for these expectations to be non-zero is that the product here will be over the same random variable, because different entries are independent. So the expected value of a product of independent zero mean Gaussian is 0. So the only terms that will contribute are terms in which you somehow match up the indices I1 and I2. And I don't want to go over the details of the construction of this matching, but it's not very hard in the case of 4 to see what is going on. You have to match the indices in such a way that all the products involve random variables that are the same. And when you do that, you get all sorts of diagrams. So this is a particular matching in which, in fact, all the indices are the same. So I1 equal to I2 equals to I3 equals to I4. This is what this diagram is telling you. If you just follow a particular index and you see where is it linked, each link is an equality. So, of course, in this case, what will be the weight or what will be the contribution of such pairing to the total sum? Well, you have n choices for this particular index. And then in each pair, you pick up a factor of 1 over n. right? Because our random variable had variance 1 over n. So the total thing has weight n times 1 over n squared. And that's it. And what I want to emphasize is that it turns out that the weight that is attached to a diagram depends only on the difference between the number of vertices, in this case there is one vertex, and the number of faces. So it depends on the genus of the surface you could construct starting from such a diagram. Here is another diagram that involves a different pairing. So in this pairing, I1 is equal to I3, I2 is matched with itself, and I4 is matched to itself. So it means you have 3 choices. So the weight is n to the power 3 times 1 over n squared. And again, here, if you compute the number of vertices minus the number of faces, you get minus 2, which corresponds to genus 0. And if you go on and write now additional moments, so if you now try to write down not just the moment of the trace of x to the power 4, but trace of x to the power 4 to some power, you get expressions like that. And when you try to do it, to expand this in terms of these finite diagrams, what you discover is that you have to sum over graphs, over what physicists call fat graphs, with number of vertices corresponding to the power n that appears here. And formally, and I say formally because it's not clear that what is written in the right-hand side makes sense. So formally, if you try, for example, to look at a non-Gaussian law, so a law in which you will have the trace of t times a to the power 4, which will make your matrix non-Gaussian, by this kind of reasoning, you would expect that it is equal to what is written on the right-hand side, and the right-hand side is just a generating function where CNG just enumerates a number of diagrams, of connected diagrams, that have genus G, n vertices, and degree 4. The degree 4 is coming from the fact that I'm looking at A4. And you can imagine for yourself that if you put instead of A4 other powers, or a mixture of other powers, you get different enumeration problems. Okay? Now, this is formal. This has been justified. So before I say that, one comment is that you see also that the leading order contribution corresponds to G equal to 0, because all other terms will have n to have some higher power. So as n goes to infinity, the leading contribution would be from G equal to 0 surfaces. And there is work of McLaughlin and Ercolani that makes this rigorous in the case of one matrix under a certain, under appropriate assumptions. And now, why would you care about multi-matrix models? So let me remind you what that means. I go back to the original slide I had put here. So in this original slide, you have a polynomial of A1 up to AD. What does this model? Well, it models interaction. Suppose at each vertex of this planar graphs, you have 2 values, +1 or -1. Then you get what the physicists call an Ising model on graphs. And the strength of the interaction is modeled by the interaction terms in the polynomial P. Okay? So, what kind of interactions people have looked at? Well, there are many such interactions, but I want really to discuss today the simplest one, which is exactly an AB interaction. So this polynomial P that appeared over there is now composed of a sum of non-interacting terms, plus the simplest interaction you can imagine, A1 times A2. And as I mentioned, this comes about in physics as under the name of Ising model on graphs. You can invent more complicated models in which you would have a Potts model or matrix coupled in a chain, and et cetera, et cetera. So there's a whole zoo of extensions of this basic model, but really I want to focus today on this one. Okay. Now, I did not come to this topic from these physics models, I came to it rather from a question in communication theory. So forget a moment about these matrix models. Here is a situation that appears in communications and in statistics. Suppose you take a matrix xn. For simplicity, let's think about n and m being the same in the discussion here. So a square matrix, n by n matrix, that is now not having any symmetry constraints, and multiply it by a diagonal matrix dn, and then by the transposed or complex conjugate, depending on whether it's real or complex. Okay, so what you get is a symmetric matrix. You can again talk about the spectrum. And it turns out that this matrix is playing an important role both in statistics and in communication theory. In statistics, it comes about when you are doing multivariate analysis of covariance matrices. So you have dependencies that are modeled by this dn matrix. In communication systems, you are talking about multi-user communication. So you have think of a cellular network in which there are many users trying to communicate among themselves. The matrix X is telling you something about the link between different transmitters and different receivers. The matrix D is telling you something about the powers of each user. And the eigenvalues or the spectrum of this matrix is very important for the performance of your communication channel. So the question, it's actually not a very complicated reduction to reduce the engineering question to that one. And now, as I said, you want to know the spectrum. Well, you can do a change of coordinates in order to try to find out the joint distribution of eigenvalues. So you move from the coordinates of the matrix XD, X star, to the spectral decomposition. And what you discover when you do that is that you have things that depend only on the eigenvalues. If the matrix D is diagonal, because of rotational symmetry, the eigenvalues and the eigenvectors are independent, or statistically independent. That has to do with the Gaussian nature. So it's just the fact that if you multiply a Gaussian matrix and you do a random rotation on a Gaussian matrix, you still get the same law. So this immediately tells you that you get independence between eigenvalues and eigenvectors. But in the case that you have this diagonal matrix Dn in between, you have this funny integral popping up, which tells you that you cannot forget about the eigenvectors. You cannot really forget about the eigenvectors when you try to compute the joint distribution of eigenvalues. You somehow have to integrate over the angular variables. And this integral is of the form, this integral is over, say, the orthogonal group, and it's of the form written up there, where Dn is the same matrix Dn that appears originally. You see that if Dn is an identity, this integration is particularly easy to perform. Because if Dn is the identity, u star goes away, the integrand is a constant, you can push it out of the integral and you're done. But in the general case, you somehow have this integral sticking into the computation. So we have this problem, lambda a1, a2, and we have this problem. And in both of them, this integral is going to play an important role. Why is that? Because when you try to analyze what is happening here, do the polar decomposition for a1 and a2, do again the spectral decomposition, write a1 as a diagonal matrix multiplied left and right by a rotation, then you see that the interaction term is exactly of the same form as something like that, where u now is just the rotation of one matrix or one basis of one eigenvector basis of matrix A1 with respect to the matrix A2. So you get the same object in both problems, and this is really the starting point of what I want to describe. So let me put it here. So that's what we want to do. We want to be able to compute what is happening to this integral, which is the same integral that appeared there. And in general, what you have two matrices, A and B, whose spectrum you assume known, and you want to understand how does this integral behave. Those are diagonal matrices. You want to understand how does this integral behave. So what exactly do you need? Suppose you know the following. You have two matrices A and B, the same that we have over there, whose spectrum, whose spectral measure converges as n goes to infinity. So I call the spectral measure one of them mu A, the other mu B. You would like to be able to prove this simple-looking asymptotics, that 1 over n squared log of this integral converges to something that depends only on mu A and mu B. As a side remark, I should mention that you could, at this point, ask yourself, why is the scale n squared appearing here? And there are many different arguments for that. The simplest is maybe to apply certain concentration inequalities, certain concentration derived from log Sobolev inequalities for the Gaussian measure, to deduce that the actual scale, the actual exponential scale you should be looking at is n squared. Okay. So suppose you can show that. Suppose you can show that you have this kind of performance. Then I'm telling you that it is not very hard to go back to the original model, the easing model on surfaces that I described before, and to prove that the partition function, the asymptotic limit of the partition function, solves this variational problem. So this variational problem has a few terms. The first two terms are something that I will call a non-commutative entropy. I'll explain something about it in a moment. They first appeared in the work of Voiculescu on free probability. The next two terms are just the polynomials, the non-interacting terms. This is what you would get if you had no interaction at all. This is just coming from the polynomial in the exponent. And then you have this Itzikson-Zuber contribution, this function j. You have to minimize over all pairs mu a and mu a1 and mu a2, and you find the partition function. And of course, those of you who have seen computations of partition functions before know that the values of the mu's that minimize this partition or maximize this expression actually are going to be the limits of what you see under such a model. So if you take this Ising model in which you have the interactions that I described, you have mu a1 and mu a2 as the spectral measures of the matrix a1 and a2. Then as n goes to infinity, the spectrum of these matrices will tend to the maximizers of this variational problem. And an interesting open question in this business is there a phase transition? And the answer to that is not known mathematically. So in particular, you can imagine that at some values of the interaction, you will have a phase transition, which means that there is more than one possible minimizer. And in other values of the interaction, if the interaction is very weak, actually there will be just a unique solution to this variational problem. And that's one of the main questions that are still open that one can next try to address. I'll say something about that at the end. So let me make a remark about these entropy terms before I proceed with the analysis of the Itzikson-Zuber integral. So you may wonder, suppose there is no interaction, what is this funny logarithmic term? Why did it appear, and how comes this non-commutative entropy play a role here? Well, if you have no interaction, you can easily, you don't have any integration over spherical variables. All you have are the joint distribution of the eigenvalues. And if you perform the change of variables, you compute the Jacobian in the change of variables, you discover that you have a van der Monde determinant popping up in the joint distribution of eigenvalues. So what the expressions that I wrote up there, and I realized that I forgot to write what is delta, so delta of lambda is just the product of lambda I minus lambda j. I don't know if it's written anywhere, but this is what it should be. So if you do the joint distribution of eigenvalues, you pick up such a term. Now, if you exponentiate, and this beta is equal to 1 in the real case and 2 in the complex case, if you exponentiate everything and you write everything in terms of the empirical measure of eigenvalue, what I call Ln, which is just 1 over n sum of Dirac at the eigenvalues, what is really written is a this product of lambda I minus lambda j becomes a sum of logs of lambda I minus lambda j. So this is a double integral with respect to the empirical measures of the log function. And if you believe in justice and that everything should behave tamely as n goes to infinity, so if Ln converges to a measure mu, then what you will pick up from this double integral is exactly a term of that form. Okay? So it's very natural to expect this term in the variational problem, and indeed it does appear. This was shown in the case of no spherical integration by Benarus and Guionnet in a work in which they derived the large deviations for this problem, but by techniques that are quite different from what I'm going to describe to you next. Okay. So we now know what we want to do. We want to go back to these Itzigson-Zuber integrals. So let me make now one comment. So if you are in the unitary case, there is an expression for this integral. You can actually perform the integration and write it as a determinant. And this is a result. It's a particular case of a formula of Harishchandra. And when you do that, you think that you have finished your problem, because you have an essentially explicit formula. The determinant involves only n factorial terms. N factorial is completely negligible in the scale exponential of n squared, because n factorial is n log n in the exponent, so you can forget about the n factorial terms. So you can just look at the maximal term. And that's your first reaction. And when you do it, you discover that the answer is not what you get by this argument. So there are several cases in which you can actually compute. And in these cases, this argument that I told you takes the maximal element, provides an upper bound, but it does not provide the correct answer. So there is a lot of cancellation going on in this determinantal formula. There are terms with different signs that almost cancel each other. And therefore, I don't know how to make any use of this Harishchandra formula in this context. Okay. So, what do we want to try to do? In order to explain the next step, let us suppose that we are in the following situation. Suppose that I take a Wigner matrix. Again, let me remind you what a Wigner matrix is. A Wigner matrix is a matrix, a Gaussian matrix, independent entries, except for the symmetry constraint. And I add to it a diagonal matrix. Okay? So I have taken a big random matrix, and I added to it a diagonal non-identity matrix. The first question you can ask yourself is, what can I say about the spectrum of the sum? Okay? So in general, you know that if you have two matrices and you sum them, there are systems of inequalities about the spectrum of the sum, but there is no way you can say exactly what is the spectrum of the sum based on knowing the spectrum of the summons. However, in the case of random matrices, that is not true. And you can prove, and this was done by different people using different techniques, you can prove that the spectrum of xn plus dn converges towards a particular limit that can be expressed as an operation involving the semicircle law, which is the limit of the spectrum of xn, and the spectrum of dn. And this operation is called free convolution. It was proposed by Voiculescu in this context. I mean, the name is coming from the work of Voiculescu, although you can see this thing done by the Russian school by different techniques, by resolvent techniques. So in particular, in the work of Pastur and Marchenko, you can find this kind of claim. But we are not interested just in limit laws. We are not interested in limit laws. We are interested in exponential asymptotics. So when you do exponential asymptotics, you have to wait between the limit, the value of the limit, and the probability of the limit. So before you get to the limit, you have a certain probability to find the spectrum in different places. You have an exponential weight. So you have to match the probability of finding your matrix in a certain region with the exponential weight. And this is exactly the topic of large deviations. This is a glorified way to describe what large deviation does for you. It allows you to weight the probability of certain regions of your space with an exponential weight and decide which region is winning. And this is leading to variational problems. So suppose you could say something about this probability. So what is a probability that this measure of the sum is near a particular value mu? Not the limit that you expect, but another value mu that later will be weighted by the exponential weight. So if you could do that, okay, I don't really expect you to follow what is written here line by line, but morally, what is written here is that if there is justice and you can do that, then you can reduce the question of computing Isingson-Zuber integrals, which is what is written in the top line, in the top two lines. So here you have the value j that I was talking about and the Isingson-Zuber integral here, to computing something involving a square, u du star minus dn squared. Now, this is very easy to understand. If you take the square, you open the square, what do you get? Well, you get the matrix dn squared, that you know what it is. You get the matrix lambda I squared, that you know what it is. And then you get an interaction term. And this interaction is exactly the Isingson-Zuber interaction. Because it will be u d lambda I, u star times dn, which is exactly what we had in the Isingson-Zuber case. So, by this simple trick, if you can solve for the exponential scale of probabilities of such objects, you can solve the Isingson-Zuber question. Okay? Now, this is a question that people coming from large deviation feel much more comfortable about, because integration over spherical variables is something foreign to us, but computing probabilities of rare events is what we make our livings from. So this is a question. We want to compute the large deviation, so the probability of atypical behavior of the spectrum of xn plus dn. And unfortunately, I cannot do that. So I cannot solve this problem. It's a hard problem. I can only solve, to a certain extent, a harder problem. So what I'm going to do is to say the following. I don't really have tools to deal with xn plus dn. Because if I want to deal with it, I'm boiled back to integration over spherical variables. That's where we started from. So what I'm going to do is to add artificially some time into the problem in such a way that at time 0, I have only my diagonal matrix dn, that I know everything I want to know about. And at time 1, I'm in the previous situation. So remember what was xn. xn is a Gaussian matrix. There is a very simple way to achieve that. Replace each entry that is a Gaussian random variable by a Brownian motion. So a Brownian motion is a stochastic process, a Gaussian stochastic process. At each time t, the variance is t, and the random variable is Gaussian. So at time 1, if I take xn to be a Brownian motion, I will get my Wigner matrix. At time 0, since the variance is 0, I'm at 0, I have dn. So now I can ask the following question. I want to evaluate not the large deviation for time 1, but for the whole trajectory. Okay? So I have my trajectory, my path of measures. At each time t, it is just the measure, the spectral measure of the matrix xn of t plus dn. I have this path, and I want to understand the spectral measure of that path. Okay, so how do you do that? I said you add time. The point is that if you deal with Brownian motion, you have time, you have tools that allow you to compute the expectations of complicated objects and to see how they evolve with time. And this is called Ito's formula. Basically, if you have one Brownian motion, if I have a Brownian motion and I want to know what is the expected value of the Brownian motion square, I can either compute it directly, or I can say, well, let's write a differential equation, not for the Brownian motion, but for the Brownian motion squared. Ito in the late 40s taught us how to do that. And then you can take expectations on this differential equation. Now, in the case of W squared, this is maybe not needed because all of us learned in undergraduate probability courses how to compute the expected value of a Gaussian variable squared. But if you have a slightly more complicated object, then maybe using dynamics is a good idea. So this requires you to develop some machinery, and this luckily was developed by Guillaume and Thierry Cabanal-Duvillard. So here is the result. Let us look at the empirical measure of, so this is a spectral measure of the matrix xn plus dn, now as a function of t. And let's apply to it a test function of both t and x. So what we get now is a real variable, which is, you can use functional calculus to write it as a trace of f of this matrix. Okay? And now differentiate. So when I write this kind of bracket, this bracket is just taking hitting this measure with the test function f, which is the same as writing, it's a glorified way of writing the trace of f of the matrix. And now differentiate. So when you differentiate and apply Ito's formula, everything is finite dimensional here. So it's just an exercise in bookkeeping. You have to make sure you understand where all the terms in Ito's formula come around, and you do this bookkeeping. And what you end up at the end is something that involves something very nice that you understand very well, because it involves an operation on f heated by this empirical measure, mu. There is a martingale. So a martingale is a process which has zero expectation, and more important, the increments given the current position have also zero expectation. That's what a martingale is. And then you have a funny term that is not linear in L, as usually we are used to, but that is quadratic in L. So you don't have a linear operation on your measure Ln, but you have something quadratic in Ln, but still involving a test function that is not f, but some operator over f. Okay? Now, the appearance, the emergence of this quadratic operator should not surprise us, because we already saw that in the one matrix case, we do get quadratic operators, we do get operations that are quadratic in the rate function. That was a Voiculescu entropy. So we should not be surprised that when we apply dynamics, there are still quadratic terms. Okay. So if you, let me put that here, because I'm going to need that. So if you now define a certain functional based on that, which is forgetting about the martingale and forgetting about the negligible terms, what you see is that this expression here, this is what is called exponentiating the martingale. You take a martingale, you take the exponential of the martingale minus a certain process. This is also a martingale. And you have constructed a martingale based on the empirical measure. And not only one martingale, you've constructed a family of martingales. So for each test function f, I give you a martingale. I give you an object that you know that, for example, you can compute the expectation of. You know that the expectation of a martingale does not change with time. Expectation at time 1 and expectation at time 0 is the same. So we have this family of martingales. And let me show you how, just from this consideration, immediately you can get an upper bound on the probability that you want to compute. So this is the martingale we constructed. And remember the property that the expected value of a martingale does not change with time. It's the same at time 0 and at time 1. And in particular, for this martingale, at time 0, the expectation is just 1, because there are no integrals. So you want to compute the probability that your empirical measure is in some ball around a path. That's what you want to do. You want to compute the probability of the trajectory. Then write it as an expectation and multiply by the martingale and divide by the martingale. So you have done nothing. You multiplied by m, you divided by m minus 1. Now, if there is justice, and in this case there is justice, you can replace in the martingale, since you are in a small ball around nu, you can replace in the definition of the martingale the actual empirical measure by the center of the ball. Because you know you're in a small ball around that value. So you get an expression that involves the center of the ball times the expected value of the martingale. And that's an upper bound because I eliminated the indicator. Okay? But the expected value of the martingale is 1. So what I got is an upper bound on this probability in terms of a certain expression involving the center of the ball, something completely deterministic, and a test function f. Now all that is left to do, optimize over the test function f, find the best upper bound you can find, and this is what you would find. And this technique is coming really from the study of hydrodynamic limits in large deviation, a technique that was developed in the late 80s and early 90s, and in this context by Varadan and others. Okay, so you get an upper bound like that, and I will skip, or maybe let me just say one more thing about that. This variational problem is very nice because this variational problem is a difference of something that is, I mean, it's a linear function in f. So for each f, what you get is something quadratic in u, but linear in f, except for this quadratic f prime f prime term. And therefore, you can rewrite this value as a supremum of a ratio. And this shows that if the value is finite, if you get an upper bound that is not trivial, then you can represent the solution of this upper bound, the solution of this variational problem, as an inner product with a certain function g. Okay? Because it's a bounded linear function. Okay, so once you know that, this gives you an idea how to derive a lower bound, a complementary lower bound. Again, this is an idea that is coming a lot in this theory. And it says, well, let us, instead of looking at the original measure, let us look at a new measure that will make use of this function g. In the probabilistic language, this means modify the drift. And I don't want to bother you with the details, but let me just say that the result of doing this operation is the following. You get, oops, yes. What you get is that if the equations, the starred equations are, so remember, S01 was this complicated functional I defined. And if you have a measure nu and a field and a g, a function g, such that this equality is satisfied for every f, and the solution is unique, so there is a unique nu that satisfies this equation for the given g, then you get a lower bound. Because, again, in probabilistic language, under the changed measure, under the new measure that exploits g, limit points are going to be your measure nu. This is not very hard to verify. And then comes, so up to now, this is more or less standard. And then comes a really nasty part that I learned from Noga Alon yesterday, that you should not discuss in public. So this works very well for nice measures nu, and nice measure nu in this particular case means that the function g has some nice property. The Fourier transform of g has some nice property, so that you can prove uniqueness of this equation. Unfortunately, this is not good enough, and what you need then to do is to work hard and show that somehow these nu's are good enough in the sense that you can approximate every nu you care about by one from this class. And as I said, I'll skip you the details, but the result of the analysis, when you put it all together, what you get is the following. So the Itzigson-Zuber integral is given up to terms that you know by the solution, by this transport-like problem. So why do I call it a transport-like problem? You have a functional I that is a functional of the path of measures. You have initial condition mu a, which is the condition you start at, right? This diagonal law that you start at. And at time one, you know where you want to be. You want to be in measure mu b. So all you have to do now is to minimize the this variational question subject to these initial and final conditions. Formally, if you define quantities as I do here, you can write Euler equations, and I emphasize formally because this can be justified only under very restrictive assumptions. So if you make an appropriate change of variables, what you get is this system of equations that were suggested earlier in the physics literature. So these equations that were suggested in the physics literature are really seen as the Euler equations for the variational problems that I described to you before. Now, this actually can be made rigorous, even these equations. So this is work of Guillonnet, it is subsequent to what I'm describing here. So if mu a and mu b are compactly supported, then you can show that the functions rho and pi that appear here in these equations are smooth in the interior of their domain. There is a very delicate question about what happens at the boundary of the domains, because all these measures are going to be compactly supported. And therefore, the boundary, you cannot expect too much smoothness at the boundary, and actually that's the source of most of the technical headache. And in fact, you know slightly more because of the analysis that I described to you. You know how these paths are realized. You know how these measures mu are constructed. And these measures mu are constructed in the following way. You can write them as the sum of the following three terms. I don't have time to describe exactly what is written here, so I'm going to cheat a little bit. Think of A as being a large matrix whose spectral measure is close to the limit measure mu A. Think of B as being another measure, large matrix. And think of S as being some kind of analog of a Brownian bridge. So it's some kind of a Brownian motion conditioned on the fact that at time one, it is 0. except that it's not a Brownian motion, it's a large random matrix. So really think of S as being a Wigner matrix conditioned at time 1 to have spectrum at 0, all its spectrum, all eigenvalues close to 0, to be very small at time 1. So you can prove that any solution to these variational problems that I described look like that. This seems to resolve completely all questions because this is a very explicit problem, except, and in fact, you also know that S, this Brownian bridge, is independent of A and B. So you feel really happy. But the big question here that one would like to understand and that we cannot understand is what is the relation between A and B? I never said that A and B are independent, and in fact they are not. So you know the marginal law of A, you know the marginal law of B, but you don't know much about the interaction between them. And all the degree of freedom in the solution is there. You don't know how to construct actually the relation between A and B. But already just from this fact, you can write certain PDEs for the solution of the matrix problem. So let me just flash what kind of PDEs you get. So think of rho as being the transport between A and B, the transport of the measure. Mu is a measure, rho is a density, and you get this system of equations giving you, for the solutions of the variational problem coming from the matrix model, the realization of the minimum. Unfortunately, these equations seem to be not well treated in the literature, and in fact, not that much is known about their solution. As I say, the most delicate part is the fact that they have compact support, and the behavior near the support cannot be too nice, near the boundaries of the support. Okay, let me conclude by mentioning some some questions that need to be resolved in this question. So the first one is, I already mentioned, we don't know too much about the analytic solutions, the analytical properties of solutions here. This is important if you want to show, for example, that strong solutions exist everywhere up to the boundary, etc. Physicists, of course, have not waited for that. So physicists have formal ways to describe solutions to these problems based on formal saddle point analysis. So they are looking at these exponents, they are doing saddle point analysis. Now, this is a little bit buzzing because this reminds you of the problem we had when we started looking at the determinant. This saddle point analysis do not really take care very well of cancellations. And they just disregard it. And they get solutions. And it's not completely clear what is the relation between these solutions and the PDEs that I'm writing here in general. The other question already at this stage is prove or disprove the existence of phase transition and say something about what happens at phase transition. So this is widely open. I mean, we are very far from understanding this phenomenon. Then there are questions that are more of technical nature that I have not described at all. This system of equations here really was using very strongly the fact that it's a quadratic functional and an A-B interaction. There are problems in which, for example, pots with more than 3 values, in which a certain convexity needed is lost, and then you cannot really use the techniques for deriving this, but this is more technical. I don't want to say much about it. And finally, of course, another goal would be to recover a result of the type that I described before concerning map enumeration, this very nice generating function formula proved by McLaughlin and Ercolani, but in the case with interaction. And of course, although large deviations have been used in much simpler contexts to get fine asymptotics starting from coarse asymptotics, we are very far here A crucial first step is, of course, to know something about the analytic properties of the minimizers. You cannot move really without that. Okay, so I think I'll stop here. Thanks for your attention.